Welcome. This is Kevin Tolly, founder of the Tolly Group, and today we will be talking about testing that Tolly conducted of the Dell Force10 distributed core fabric architecture. That testing focused on architecture scalability, resilience, and power consumption for a design yielding 384 user-facing 10 gigabit Ethernet ports. The full test and associated configurations are detailed in Tolly Report 211129. Joining me in the discussion today are Dell Force10 Senior Director of Marketing, Jeff Baher, Dell Force10 Technical Marketing Engineer, Jaiwant Virk, and the project's lead engineer from the Tolly side, John Tolly. First, let's ask John to give us a high-level summary of the testing and the results. Good morning, John.
Good morning. The test of the Dell Force10 distributed core fabric architecture was conducted in September 2011 and revolved around illustrating the architecture's scalability, resilience, and power consumption. The test comprised of a 10-node configuration based around the Dell Force10 Z9000 data center core switching system. The Z9000 is a 2RU Layer 2-3 system equipped with 32 40 gigabit Ethernet ports. In the test, we constructed a non-blocking leaf spine configuration using 6 Z9000s as leaf nodes and 4 Z9000s as spine nodes, interconnecting via 40 gigabit Ethernet. As configured, this design yielded 384 user-facing 10 gigabit Ethernet connections intended for data center server and storage connectivity. Once configured, we measured the system reliability and total power consumption. We also evaluated the architecture's ability to scale beyond our test configuration. Tolly engineers evaluated how the Z9000 distributed core responded to a failure of an entire spine node and quantified both the failover and failback times between ports on different leaf switches. Tolly engineers initiated a bidirectional stream of 512 byte packets at the rate of 100,000 packets per second from the first port of leaf switch 1 to the last port on leaf switch 6. So, port 1 to port 384 of the logical switch. There were 1,000 routes present in the fib that would need to reconverge after the failure. The routing of traffic across the spine is dynamic. In this case, engineers determined that the packet stream was traversing spine switch 2. Using a software command, that switch was taken offline by disabling all ports. Engineers measured how many packets were lost before the stream was rerouted over a different spine switch, and used that data to calculate the failover and failback times. On average, the failover and route reconvergence occurred in 1.2 seconds. Rapid failover prevents user applications from timing out. In this case, affected users might notice only a small delay before their applications resumed responding, or might not even notice anything out of the ordinary. Once the switch was restored to operational status, the failback occurred in just 1/100th of a second. It is important to note that these tests were run with an engineering build of the switch code, and that Dell Force10 personnel anticipate sub-second performance with ready-to-sell production code. Power consumption is a key element of recurring expense for any data center, and can be a significant element of total cost of ownership for switching infrastructure. The power consumption of switches will vary depending upon the workload, i.e. traffic on the switch at any given time. It is important to note that power consumption comparisons must only be made between systems running identical traffic loads. The 225-member Alliance for Telecommunications Industry Solutions has developed a standardized methodology for measuring LAN switch power consumption. The specification for core switches mandates that the tester measure the power used when processing a mixed load of traffic at 30% and 100% utilization, as well as the power used when the switch is idle, i.e. no traffic. These values are combined in a weighted average to provide the ATIS measurement. The Z9000 switch delivered an ATIS power measurement of 407.37 watts. In addition to resilience and power consumption tests, we also evaluated the ability to scale the distributed core fabric architecture beyond the 10-node leaf spine configuration. We found that the architecture is in fact pay-as-you-grow and can be scaled in non-blocking configurations with up to 32 leaf nodes and 16 spine nodes, yielding a total of 2,048 user-facing 10 gigabit Ethernet ports. Additionally, in speaking with Dell Force10 personnel, we learned that even larger systems can be constructed when using 10 gigabit Ethernet interconnects. In this manner, a total of 8,192 user-facing 10 gigabit Ethernet connections can be achieved.
Thanks, John. And now let me welcome Dell Force10 Senior Director Jeff Baher and Technical Marketing Engineer Jaiwant Virk for our question and answer segment. Jeff, Jai, Thanks for joining us. Jeff, tell me a little bit about the motivation behind the distributed core fabric architecture.
Well, that's a good question, Kevin. For starters, we've come to learn that not all data centers are created equal, and especially with emerging workloads such as Hadoop, new architectures are required to accommodate greater and greater amounts of east-west traffic versus the more traditional north-south traffic patterns that we've observed historically. This requires a lower latency, non-blocking east-west connectivity solution that's capable of scaling out as workload performance requirements dictate. This is exactly what the distributed core fabric architecture is designed to do.
Jai, when it comes to data center core switching, conventional wisdom is to use chassis-based solutions. What makes the distributed core architecture viable as an alternative?
Kevin, when you look at our distributed core architecture, there are three distinct components: spine nodes, leaf nodes, and interconnect cabling. In chassis terms, the spine nodes can be viewed as switch fabrics, the leaf nodes as line cards, and the interconnect cabling as the backplane. Now from this view, we've simply modularized the traditional chassis system. But in doing so, we were able to scale the system well beyond what's available today in a conventional chassis. If you consider that a distributed core system can scale up to more than 2,000 user-facing 10 GB ports today, that's roughly 3 times more than the highest density conventional chassis, whatever is available in the market today. And the chassis is inherently more reliable. With a conventional chassis deployment, what you need is actually two chassis just for reliability and high availability for bandwidth, optimal usage. And at that, a node failure in a chassis architecture would result in almost a 50% loss in capacity. A node failure in a distributed core architecture, in contrast, is far less catastrophic, resulting in only a fractional degradation of performance.
Gentlemen, thanks for those insights into the Dell Force10 distributed core fabric architecture. As we close, I'd like to remind our listeners that the full details of the tests discussed today are found in Tolly document 211129, which can be downloaded from both www.tolly.com and www.force10networks.com/Tolly report. Thank you everyone for listening, and goodbye for now.